secondary heat generating components, namely some flash storage and some power circuitry. Making sure that these components get access to the cooling ability of the water block will ensure that they're kept as cool as what they were designed for, maybe even cooler. And to do this, I'm simply using some copper strips and thermal glue, with the accompanying components receiving standard thermal paste to prepare them for mounting. As for the SoC, that needs a new coating of liquid metal for better thermal bridging, and to prevent overspill I'm tracing its perimeter with putty to seal around it, much like on the original heatsink, with the same being mirrored on the copper side. To ensure that it makes good contact, I'm using the original rear bracket to put downward pressure on the back of the processor, and in addition to that there are some components on this side of the board that also need some thermal bridging, though this time to a lid that I've not made yet. These aren't particularly power hungry components, so having the heat dissipated to a lid should be quite adequate for them. But this isn't the case at all for the VRMs, which are in a row right here. These regulate the power input, and as a result they generate too much heat to be dealt with passively by the lid. On the original PS5s, Sony kept them cool by using a heat pipe to link them to a small heatsink. A heat pipe, for those who don't know, isn't just a rod of copper, but is actually hollow with a wick covering the internal surface. As there's a liquid inside that has a low boiling point, this liquid evaporates from the wick whenever heat is applied and then moves as a vapour to cooler areas where it condenses again before soaking back into the wick where the process starts all over again. This moves heat rapidly and effectively, but the shape of the original won't fit my new design, so I'm going to have to make my own. Thankfully it's fairly easy to buy brand new heat pipes online, and after warming it up it's possible to bend it fairly easily into the required shape. What's not so easy however is soldering heat pipes to anything, as if you heat them up too much they can explode. Cooling one side with a damp cloth though worked for me, and I was able to mount it to the original copper spreader. All this, by the way, is what the additional mini water channel is for, as it cools a stack of copper, which in turn cools the heat pipe. And with that, all the thermal bridges have been made and it's looking pretty slim, but there's a big problem that could spoil the party. Where's the power supply going to go? As you've seen already, it's kind of big and a bit of a weird shape, and it begs the question, where have Sony put the power supply in their past slimline consoles? Well, in the past two PlayStation Slim releases, they drastically lowered the console's overall power consumption, which meant that their internal power supplies could be much smaller, though capable of delivering far less power. Unfortunately for us, there's no way we can reduce the PS5's overall power requirement to allow the use of these smaller power supplies, but there is still one option we can explore which Sony and other console makers have resorted to in the past, making the power supply external. Both the PS1 and PS2 Slim offloaded power to an external power brick to make them smaller, a strategy also used in several Xbox consoles as well. While it's not ideal, we are trying to push things to the extreme here, so it's a compromise I'm willing to make. In order to prepare for this, I need to solder some really thick wire to the PS5's power input to reduce the voltage drop down its length, and routing it around to exit between the barbed connectors allows me to hide it between the two lengths of rubber tubing that will carry water to and from the cooling block. This stuff is a bit thicker than I'd like, but at least it's nice and robust, and to match it aesthetically with the rest of the build, I thought it would be cool to sheathe it with some copper braiding, which also provides grounding to the chassis. So with that done, we're ready to add the lid. Earlier I used the cooling block as a template for making this, using the last bits of copper and soldering them together, which ended up looking pretty neat. While I am going for a minimal look here, I do need to make some holes for the USB ports, and also for a power button. As I want to make this power button also act as a power light indicator, we can take the PS5's original lighting strip board and glue a brass tube over its LEDs with some epoxy. The LEDs should light up this epoxy, which will be visible through the tube, but we'll have to wait until later to see how well this works. As the LED board itself doesn't actually feature a button of any kind, some glue can be used at the other end to anchor it, so that when pressed it can trigger a little push button mounted behind it like so. This push button in turn is wired up to the original power button and will thus trigger the PS5 to turn on or off when pressed. As I earlier soldered some brass pillars to the internal corners of this cover, it can be screwed in place from underneath, with some rubber pads providing some feet here as well. To tidy up the rear side, it has its own special cover, and to make the tubing look a bit neater, I've used my trusty prusa to print off a few plastic brackets to clip it at various points, essentially turning it into a tether. Despite being fairly bulky, it's not really that noticeable when the unit is in position, especially as, like most set-top devices, it will have other cables like HDMI going into the back of it anyway. Either way, it looks great in my book, and the polished copper provides a unique, refreshing aesthetic. The best bit, of course, is that it measures just 1.9 centimeters. We've actually beaten my 2 centimeter goal, and it's now a fraction of the thickness of the original. Crazy. Before we can turn it on though and test out whether the cooling block performs well enough to keep the system cool during use, I do still need to sort out a power supply, which, as you know, is inspired by previous PS5 Slim releases. The only difference with mine is that it's going to have to handle cooling as well, which makes things challenging but also very interesting. So with these tethers now added, I need to make a power brick that can not only provide power for the PS5, but also cool it as well. Now in terms of power, the power brick that was originally inside the PS5 is not only a super weird shape, but it doesn't feature its own fan, instead being designed to rely on the console's own airflow to keep itself cool. Strapping a fan onto it to keep it cool just looks stupid, so ideally I'd like to get rid of it and use something else entirely. Taking a close look at its specs, we can see that it outputs 31 amps at 12 volts, and thankfully it appears to present this voltage without being connected up to the PS5. So, in theory, we can indeed swap it out with any sufficiently powerful 12 volt alternative. I have this much more sensibly shaped computer power supply on hand that'll do the trick. And to make it a bit prettier, I've made a case out of aluminium to go around it, though you might be wondering why it's so long. Well, that's to make room for the cooling components. After adding some fans to push air through it and a set of water pumps to circulate the water, it can be fitted to the casing alongside the power supply and be linked up to the PS5's new tubing. As the copper of the main PS5 body and the aluminium casing of this power/cooling unit both block Wi-Fi signals, I've extended the antennas down to be glued to the exterior of this for an unobstructed signal. While it's not the prettiest thing in the world, it actually won't ever be seen, as the idea is for it to mount to the wall behind a TV. And with that, the unit is complete and we're ready to test it out. Now, it would be a little bit of an understatement to say that I'm nervous, because I've worked on this for a couple of months, and let's hope it works. Come on. Okay, so 12 volts is being supplied to it as expected. But there is one thing that I'm hoping is the cause, which is simply that the fan isn't plugged in. After all, I've had computers before that won't turn on without a fan, so maybe that's the case here as well. But unfortunately not. Look, it's going! Ah! What I did was just, where the power lead goes in here, I just bridged the connection, so that's great because that's not that hard to fix. And we are now working. So what I've done is basically just bypass the original power button and its little strip and just solder it straight onto the motherboard, and it's working, which is great. Hey! That little beep of triumph. There we go. That's a relief. So, getting it turned on is obviously great, but the whole point of this thing was to obviously make it thin, but it needs to perform just as well as the original console in terms of keeping the PlayStation cool. So, step 1, turns on. Step 2, Need to make sure it actually works properly. So let's run some games and see if it's kept cool. Little did I know that things were about to go horribly wrong. That's not good. It's frozen. Feels okay. Whoa. This isn't where this is going to be permanently fitted, so I had it propped up on this and it had fallen over, blocking the intake, which is on the bottom here, so there was no airflow, and the PS5 presumably overheated, so let's hope it's not done any permanent damage. Come on, I'm just fed up. We've got another problem, a bigger one this time. It's now not turning on. So the light comes on and then it just goes off and there's nothing I can do to change it. And to have made such a stupid mistake right at the project's completion, killing the PS5 stone dead, is devastating. So I am incredibly disappointed, but I'm not going to give up because I actually sent over a spare PS5 to use for the B-roll, and I am going to borrow the motherboard from this to hopefully get the system running again. Anyway, the process of transplanting the motherboard isn't terribly difficult, but this time I'm including a few thermal probes so we can monitor the PS5's temperatures at various points to make sure it's all working within spec. So, with the cooling unit mounted more securely this time, it's the moment of truth. Light. Come on. Come on. Yes! Oh! At last. Woo! Now, before I do anything else, I'm going to test out the temperatures on this thing so we can hopefully avoid a reshoot of what happened earlier. So I'm going to run Horizon Forbidden West, which is a new title, and it should push the PS5 to its limits. But I'm going to be monitoring the thermals through my thermal probes. So let's hope it goes well. After leaving the game running for several hours, the first news is that it hasn't frozen this time, and checking out the temperatures we can start to see why. The main processor probe reports a maximum temperature of just 46 Celsius. As the probe isn't actually inside the silicon though, my best guess is that it's somewhere around 65 degrees internally, but still a good result. What about the memory? This one should be fairly accurate as the probe has been embedded within the heat spreader itself, and we get a result of 52 degrees here. The VRMs are even cooler at 44 degrees, indicating that the heat pipe is doing its job. Yay! So great results, but how do they compare to the original untouched PS5? Well, I positioned my thermal probes as closely as possible to how the guys over at Gamers Nexus mounted theirs when they were doing a detailed thermal analysis of the console, and there are some interesting findings here. Their processor measurement hit 75 Celsius, though again this was taken from the back, so it wouldn't surprise me if the actual silicon temperature was in the 80 degrees Celsius range at least. As for their RAM measurements, they reported that it hits 94 degrees Celsius, and that it's likely running a bit too close to its maximum allowable temperature. So the 52 degrees we're getting is really good news, as are the results for the VRMs. The original cooler, 71 degrees Celsius.
Today, we are going to push the limits of what is possible for the PlayStation 3. We're gonna dissect this gaming legend, give it a whole bunch of upgrades, and overhaul its cooling system to figure out just how much performance we can squeeze out of this thing. for science, of course. See, the problem with modern hardware is that it comes really aggressively tuned from the factory. Outside of a few choice examples like the Nintendo Switch here, you're unlikely to get anything more than a 3 to 10% boost in performance by modding your system. Now, this is good in a lot of ways because it means out of the box you're getting all of the performance, but back in my day, you used to be able to get like 20 to 30% more performance, and maybe even more than that just by tinkering with the hardware. And that was really fun. So I was feeling nostalgic the other day and I was researching the PS3 when I found out that you can overclock these things for really big gains in performance. In fact, they even used to sell full-on water cooling kits for people who wanted to turn things up to 11. Now, unfortunately, you can't buy those anymore, but I have a feeling that we might just be able to build our own. So step number one is going to be tearing into this console. But picking the right PS3 for this project was actually incredibly important. By my count, Sony released 19 different versions of the PS3, and they're each special in their own unique way. What we have here is a CCH2501B, and this is a Goldilocks PS3. See, later versions of the PS3 run cooler and more efficiently due to improvements in how Sony made their chips. So naturally, you might be wondering why I'm not working on a super slim PS3. If those were the last major hardware revision, then they should run cooler and be the best for overclocking, right? Well, yes and also no. They are the most efficient, but you can't overclock them due to changes that Sony made in their security setup. Hence why I'm working on a middle child. This is the most efficient generation of the PS3 that's still completely hackable. So now that we've got this thing completely torn down, let's take a closer look at those chips. This is for all my fellow geeks at home, but when the PS3 first launched, they used a 90 nanometer architecture for both the CPU and the GPU. This later PS3 uses a 45 nanometer process for the CPU and a 40 nanometer process for the GPU. Practically, what that means is that this PS3 uses about 50% less power than a launch PS3, and that makes it significantly easier to cool. However, this PS3, and almost all PS3s of a similar vintage, are anything but cool these days because they suffer from a serious problem. These little covers are called the integrated heat spreaders, and their job is to help spread the heat from the chips they cover to a wider surface area. On both their top and bottom surfaces, they're covered in a thermal interface that helps to facilitate that heat transfer. The problem is it dries out over time, which then leads to overheating. Now, the stuff on top is super easy to fix. You can just wipe it away with some isopropyl alcohol, but the stuff underneath, well, that's where things start to get a bit dangerous. For some reason, Sony thought it was a good idea to glue the GPU's heat spreader in place. So to help loosen it, I'm using a stream of really hot air and then just attempting to pry it off. This was super nerve-wracking though, because I had no idea how much force to use, and I wasn't sure if this cracking you're hearing right now was the glue letting go or me bricking my console. I guess we'll find out later, but removing the IHS revealed just how dried out things had gotten. Over on the CPU side of things, Sony did things a little differently. This time, they used a ring of silicone to hold the IHS in place. So that means we have to cut through it using a small knife. The only catch is if you push your knife too far in, you can again brick your console. Thankfully, this one wasn't as bad in my opinion, and after some careful cutting, I eventually got it to lift away. So after spending a bit of time removing the old thermal paste and adhesives, I was ready to install our new thermal interface, which should dramatically reduce temperatures and in turn allow us to squeeze even more performance out of this PS3. This is PGM7950, and while it might look like a sheet of boring gray plastic, it's actually the state of the art when it comes to thermal interfaces. Once it warms up, it melts into goop that is extremely good at transferring heat. So this alone should give us a huge drop in temperatures, but after I was done installing it on all the heat generating components, I was left with a bit of a puzzle. I needed something that was strong, flexible, and heat resistant to reinstall those spreaders. Enter high temp RTV sealant. It's silicone based, so it should have plenty of hold, and it can withstand temperatures of over 300 degrees. It takes 90 minutes to cure, so that gave me plenty of time to reassemble everything and make sure that those spreaders were fully compressed and making good contact with their dies below, because the tighter we can get that bond, the better everything is going to perform later. All right, it is a couple hours later. Our gasket should now be fully cured. Now, the next thing that I want to do is completely break this thing down again and then 3D scan this entire motherboard. Now, that might sound like Star Trek level technology, but in 2025, you'd be surprised at just how affordable and user-friendly 3D scanning has become. Within an hour, I can have a complete digital replica of any part that's accurate down to the width of a human hair. And that dramatically reduces the amount of time that I had to spend prototyping new parts for these old systems. This scan in particular should make it way easier for me to design a mounting solution for our new water block. But I'm getting ahead of myself. With the scan now complete, let me introduce you to said water block. Or should I say water blocks. These shiny blocks of milled aluminum are going to sit directly on top of our CPU and our GPU. Now, originally I was going to do one big block that covered both, but a weird quirk of the PS3 is that the GPU and CPU actually sit at significantly different heights, so now our setup is a little bit more complicated. But basically, the way this is going to work is water is going to flow in here, pick up heat from both chips, and then it's going to flow to the radiator where it's then cooled. So our main challenge at this point is to come up with some sort of system that is going to keep both of these in place and also compress them on top of the chips, because like I said before, good mounting pressure is key to getting good heat transfer. Now, I suppose I could have 3D scanned these as well, but some things are just easier to model the good old-fashioned way. With both the motherboard and the water blocks incorporated into the model, I set about designing that new mount. It doesn't need to be anything fancy, just a simple frame that will secure everything in place while still fitting within the bounds of the PS3's motherboard. So while we wait for our new part to print in hot pink PLA, I want to use my angle grinder to do some other modifications to the PS3. Unfortunately, the inlet and outlet ports on our new water blocks are just a little too close to this RF shielding. So to give us a little more room to work, I'm just removing a large section of it. And because later we're going to be running soft water-filled tubes through here, I took a few minutes to round over all the sharp edges with a file. With that all taken care of, I was ready for our first big test fit. But I'm sure many of you at home right now are yelling at your screens about how PLA is not an appropriate material to use for a part like this. To which I would respond that, yeah, you're right. And that's why we're only using PLA for the prototype. Now that we know that it works, we're going to switch over to carbon fiber reinforced nylon, which is significantly more heat resistant, stronger, and it's also a lot harder to print. So clearly, it passed the visual inspection. And at this point, I was super excited to install it in the system and do a bit of testing. However, I should point out that there's a serious complication to using nylon in an application like this, and we're gonna dive into that more later. But for now, I grabbed some soft PVC tubing and started connecting all of our parts. This 120mm rad might seem modest by today's standards, but it's actually perfectly sized for the PS3's heat output. To keep the coolant circulating through the system, I grabbed this simple pump with an integrated reservoir, and then finally, the last piece of the puzzle is this sick blacked out 120mm Noctua fan. It screws right to the radiator and should provide plenty of airflow to cool down the water. And now, you're probably thinking that the only thing left to do is pour some water into the loop and let it rip. But that would be a great way to kill our PS3. In a couple of different ways, actually. First, it's really important that you work all of the air out of the system by agitating the loop. Even small air bubbles can build up in the rad, stop the flow of water, and quickly lead to an overheating scenario. Second, you'll notice that I'm actually powering the pump with an external power supply. And that's because before I send any power to the PS3, I need to make sure that there are no leaks. So for the time being, I set the PS3 to the side with the pump still running and turn my attention to another important problem. We still don't have any way to power our new cooling system. Lucky for us though, the PS3's factory fan is quite inefficient and draws over an amp of current all by itself, which means that the connector that it used to plug into should provide more than enough juice for both our new fan and our new pump. The only hiccup is that in order to tap into it, we need to make our own custom wiring harness. And that meant decoding the PS3's wiring color scheme by studying a bunch of old diagrams that I found online. After stripping the wires and twisting them into what I'm pretty sure are like pairs, I was ready to do my first bit of soldering on this project. And in order to suck up all those nasty soldering fumes, I pulled out my 3D printable solder extraction fan. I call it the Zacuum, and if you want to print your own at home, you can scan the QR code on screen right now or check out the link in the video description. And if you're interested in any other tools or materials I've used throughout this project, I'll include links for all of those down in the video description as well. After sealing the wires with a bit of heat shrink tubing, I now had a sleek, simple way to power the new cooling system without the need for any external wires. And checking back in on the PS3, it had been running for well over an hour, there were no leaks, and all of the tubes looked bubble-free. So I was finally ready to reassemble the PS3 and take it for a test spin. Obviously, with all the new parts, I had to run it with its top off, but don't worry, we'll fix that soon. Okay, here we go. First maiden voyage with the water cooling setup installed. Power button. Got the beep. Fan is going, that's a good sign. HDMI 1. Is the pump going? Yeah, I think the pump is going. I can see movement in there. Oh, look, it boots. Wow, I mean, I don't know what to do. I guess it works. This is fantastic. I'm kind of speechless right now. I was expecting more trouble than this. I think the next thing that we need to do is to make this look more like a finished product and less like a mad science experiment. The easy path forward would be to just drill a hole here and here, run these tubes through the side of the PS3, and then mount the pump and the radiator externally. But that actually would create a couple of problems. The first one would be that, well, it just wouldn't look very good. But then also, a lot of the components inside the PS3 depend on the airflow from the fan in order to keep them cool. Like the PSU here, which I can feel is actually already starting to heat up just on the menus. So what I actually want to do is take the radiator and fan and mount them approximately where the old fan used to be, so that we can capture that airflow in order to keep the rest of the components inside the PS3 nice and cool. And in order to do that, I broke out the 3D scanner again. This time I scanned the semi-assembled PS3, which will allow me to create new components that fit perfectly inside of our existing envelope. Of course, I also needed to incorporate our new parts as well, and much like with the water blocks, they're pretty simple, so again, I did things the old-fashioned way. With everything now incorporated into the 3D model, I set about creating what I'm gonna call the airbox. This will sit where the old fan used to be and funnel air towards the PSU after it's passed through the rad. The airbox won't be in direct contact with any hot parts, but I still suspect it's gonna get a bit toasty inside of the PS3, so that's why I'm printing it in glass fiber reinforced ABS. This is quickly becoming one of my favorite materials to work with because it's super strong, heat resistant, and it prints beautifully on my other printers. So naturally, I was curious to see how it would print on my new P2S. And wouldn't you know it, the finished part looks damn near perfect. It's got a nice matte texture that hides the layer lines, and the supports popped right off, which is always super satisfying. The next part I printed is a lid that closes off the top of the airbox and gives us somewhere to mount the rad. It clicked perfectly in place, and now I want to pick up a thread from earlier in the video. This is a 3D printed water block that I made about a year ago, and as you can see, it's got quite a bow to it. This thing is also made from carbon fiber reinforced nylon, and removing these screws reveals that, yeah, it's permanently deformed. If this happens to our PS3 mount, it's gonna be a big problem because it means that we'll lose mounting pressure over time. And this is what happens when you don't properly anneal your parts. Stefan from CNC Kitchen just did a great video explaining this, so I'd urge you to go watch that, but I'll give you guys the cliff notes while I attempt to prevent our new mount from turning into a potato chip. I found this great 3D printable frame over on MakerWorld that transforms an AMS HT into a little oven for annealing your parts. Basically, the idea here is that by slowly heating your parts for an extended period of time, you can get them to release a lot of their internal tension that's left over from the printing process. The result should be stiffer parts that are far more resistant to long-term deformation. So after baking the part for over 24 hours at 85 degrees, my quick and dirty subjective comparison confirms that. This annealed part feels about 20 to 30% stiffer than it did before. Of course, the real test will be to see how it performs long term, so let's get it installed in the PS3. The keen-eyed among you might have been wondering what those big holes in the airbox were for, and I actually made those so that I could install these copper heat sinks on top of our water blocks. These will add a layer of redundancy and keep the system from overheating in case the pump ever fails. And then there's also the changes that I made to the fittings. Softline tubing is prone to kinking with hard 90-degree turns, so to make this setup as compact as possible, I installed these elbow fittings on both the rad and the pump, which then allowed me to dramatically reduce the length of all our runs. But one problem I haven't tackled yet is how exactly we're going to secure the pump inside of the PS3. Honestly, the solution is pretty simple. I used the 3D scans from earlier to design a bracket that perfectly fits the PSU's contours. After printing it out on the P2S, I bonded it in place using some good old-fashioned super glue, which works extremely well on most 3D printed plastics. After the glue cured, I connected the hoses, screwed the pump in place, and then confronted the reality of what had to happen next. All right, so we now have what I think is the most compact form factor possible for a water-cooled PS3. But predictably, we still have a little bit of an issue because this top cover won't fit back on anymore. So I think in order to fix that, we are going to have to turn our PS3 into a convertible, or maybe like a hardtop convertible. Using my larger Bamboo Lab H2D, I printed this really simple template that shows me where I need to cut to turn my PS3 into a drop top. Now, I do feel like this is kind of cheating, and in a second, I'll show you how you can make big parts like this even on a small printer. But for now, I pulled out my oscillating multi-tool and began cutting along the lines that I just traced. The idea here is to remove enough material that it fits around all of the new parts while still leaving all of the clips that allow it to connect to the rest of the shell. After filing down all the rough edges, I did a quick test fit, and now we can start working on covering up that big gaping hole. Back in Fusion 360, I basically just drew the smallest box possible that would still fit everything inside of it, created a rough shell, and then worked backwards from there. I matched a bunch of existing curves from the PS3, I added a honeycomb grill that will function like an air intake, I added a fill port that will allow me to keep the loop topped up, and I even added a bit of custom branding that I made in Photoshop. Unfortunately, like I touched on earlier, this new housing was too big to print on the P2S. But the solution is actually really easy. I just split the housing up into two pieces that could be printed separately, and then we'll join them together later. This is a really easy way that you can expand the capacity of any 3D printer. And honestly, the hardest part was just waiting for my prints to finish. Given their size and the fact that I was printing at a really high level of detail, all told they took close to 48 hours. But man, was it ever worth it when I saw the results. The surface quality was insane, they felt super solid in the hand, and the black ABS GF that I used is actually a really close match for the PS3's original shell. Now, to secure the house together, I used super glue, which again works really well on ABS, and then to install it, I used, well, more of the same. After a quick test fit to make sure the upper shell was still removable, I screwed everything together and then started filling the loop. This time, instead of using plain distilled water, I switched things up and used a purpose-made coolant. This stuff has a number of additives in it that make it more resistant to corrosion, fungal growth, and importantly, make it even better at transferring heat. And then, to cap it all off, I printed my last part on the P2S, which appropriately was a cap that screws in place like so. Now, before we unleash the water-cooled potential of this PS3, we have two things left to do. The easy one is replacing the original mechanical hard drive with a more modern SSD. This should provide a substantial decrease to loading times, and it'll give us a full terabyte of storage for games. And yes, I said storage for games because the next thing we have to do is hack our PS3. These days, it's relatively easy to do, if a bit time-consuming. Basically, we're using a browser exploit to allow custom firmware to be running onto the system. This is a multi-step process and ended up taking me a couple hours to do, but custom firmware allows us to do all sorts of fun stuff like rip games to the internal storage, mess around with all sorts of fun settings, and importantly, overclock the system. And that's why we're all here, right? So let's dive right into it. Back when the system was air-cooled, the CPU and GPU would hover around 61 and 67 degrees respectively. With the new cooling system, they're hovering right around 40 degrees, which is a huge drop and an excellent omen for our overclocking adventure. Unfortunately, it turns out that overclocking your PS3 is a bit of a rabbit hole. The custom firmware I'm using is available in both standard and overclocked flavors. The overclocked variant gives you a respectable 20% bump in GPU speed and a 15% increase in VRAM speed. And running this, we see that, yeah, temperatures haven't increased at all, there's no visual artifacting, and we're already seeing an increase in frame rates. But clearly, our system can handle more. So I went in search of how to do that, and I'm not gonna lie, it looked ugly at first. I found a lot of info saying that basically you have to make your own custom firmware, and that's actually really risky. If you push your overclock too far and your system becomes unstable, well then you won't be able to rewrite the firmware back to a safe overclock, and your system is essentially bricked. Thankfully, I found a solution. There's actually a slightly newer custom firmware that came out just before I started making this video. The timing of it is nothing short of impeccable when you think about how old the PS3 is. This firmware allows you to adjust the GPU and the VRAM speeds on the fly. So after tinkering around with these settings, I found that our new cooling system works really well. No matter what the clock speed is, the temperatures basically don't move. I think the highest I ever saw was 43 degrees. So with all the temperature headroom in the world, I pushed the clock speeds until the game started to fall apart. These visual artifacts are a warning sign that things are about to go catastrophically wrong. So I dialed things back from there, and I found the highest clock speed I could safely achieve was 750 on the GPU and 925 on the VRAM, which from stock is a 50 and 42% increase respectively. Obviously, that is insane, and this is exactly why I love messing around with old hardware so much. But of course, that's only half the story. So let's talk about how those new clock speeds translate into real-world performance. Uncharted 2, which is probably my favorite PS3 game, showed a huge uplift. In terms of FPS, it went from the high 30s to the low 50s, which is close to linear scaling with the clock speeds. Watch Dogs, on the other hand, was a bit of a letdown. It showed a small improvement, but it's still borderline unplayable even with the overclock. I suspect the bottleneck here might be the CPU, which unfortunately for us isn't overclockable. Don't worry though, because things came roaring back with BioShock Infinite. This game showed a 50% uplift in frames per second and was at times close to becoming a 60 FPS title, which actually did happen for another one of my favorites, Gran Turismo 6. This one was struggling in the mid 40s, but with the overclock, it's damn near locked at 60 FPS. So at the end of the day, not every game is gonna see a huge increase, but the majority of them do, especially games with uncapped frame rates. Practically, this makes games feel a lot smoother and more responsive. I'm actually kind of surprised that Sony never released overclocked Slims as PS3 Pros, because to be completely honest with you guys, I don't think it was really necessary to water cool the system. Now obviously I'm saying that with the benefit of hindsight, but clearly temperature is not the limiting factor here. I suspect you could probably get most of this performance uplift by simply refreshing the thermal interface and maybe installing a new fan. But don't get me wrong, I am still so glad we did this. Not only was it a ton of fun to figure out, and now I have this cool custom PS3, but somebody had to do it in order to answer the question of whether or not it was worth it. Now, there is one way that I could have squeezed slightly more performance out of the system, and I'm gonna talk about that along with a few other things I think I could have done better in a separate bonus video for channel members. So check that out if you're interested, and I will see you guys in the next video. Peace.
Hi, today I'll design and make something incredible, a lantern. No, wait, not a crap lantern, a magical fairyland lantern. One of those that are filled with fireflies and glow. What did I show there? The final product? Did I make it? We don't have fireflies around here, so I'll make electronic fireflies. And I want my fireflies to actually fly. So I'm not gonna buy some IKEA LEDs on a string and slap them in a jar and call it a firefly lantern. And I can't power them by hanging them from wires because they'll move around and tangle to each other. So I'll have to power them wirelessly. Let me show you. It is basically like a transformer with a primary and secondary coil, and I connected an LED to my secondary, and if I raise the voltage to the primary from my auto transformer, you can see that melts the out of the primary. You know, they say inductors block AC. No, they limit AC. You know, if someone drops you on the sun, closing your eyelids won't save your eyes. Such small inductors need to run at much higher frequency, like 100 kHz or more. Let me explain the plan. Basically, my fireflies have an inductor and capacitor that resonate at a specific frequency, excited by the fields from some bigger transmitter coil running at the same resonance frequency. So the voltage across the resonance circuit rises to a point that can turn on an LED across it. How do my fireflies fly? I'm thinking I'll just put a fan under them and blow on them to, lift them up. So they have to be light. Let's make them. This is the primary of a wall adapter transformer I salvaged a while back that has this very thin light wire suitable for my flies. Doesn't look super pretty. Let's see if it works. Okay, so I bought two LEDs to try that you may not see here. This one is yellow-green, which is very similar to the color of a firefly, but it's dim. This one is just warm white, but much brighter than the other one. I may try both and see what happens. Now, the question is if I can solder this tiny capacitor to this tiny LED. Now I provide a 50 kHz signal from the function generator of my scope to some random coil I have here. If I place that around my tiny coil here, it doesn't turn on. Nope. Hi, I'm Captain Hindsight. My friends simply call me Bless you. Shut up. Let me save you the headache. I have like 2 months worth of footage of testing and failing you don't want to see. I tested this a bunch and realized you can't make the same inductance if you increase the diameter of the coil and reduce the number of turns. But bigger coil means more magnetic fields pass through it and so more energy is transferred. Well, as long as the coil size is smaller than the coil inducing the energy. Remember, the fields have to close around the wires, not inside or outside. So I tried a bigger coil and even bigger, which helped, but then the weight was a problem too. Change of plans. I can't keep increasing the number of turns on the coil. It will get very heavy and won't be able to fly. So instead, I decided to go to a wider coil with only a few number of turns, 6.5 turns, and whatever the resonance frequency of this circuit will be, I'll tune my transmitter to match this. Okay, here we are, and I mounted the coil on a thin plastic sheet too, so it doesn't deform, and we have the capacitor and diode. Let's see. Ooh, look at that. Let's find the resonance. Whoa, okay, so I say the resonance is around 95 kilohertz. So that's what we'll design for. Now, to make the lantern, first things first, I buy a proper size glass because this is the one thing I can't make myself, and I'll design the lantern around it. And to transfer the energy, I'll put one coil on the bottom and another coil on the top. These two coils will have the same direction of winding, so same direction of magnetic fields. And with these, I'm hoping to create more uniform fields around the center of the glass. But depending on the location of my fireflies, they could see more or less fields, so brighter or dimmer. And also depending on their direction, they could turn on and off. Which is fine, it's like fireflies flying around blinking. Let's talk about the driving circuit. I'm using my beloved bistable asynchronous 0-volt crossing oscillator circuit that I used in my previous videos too. In this variation, I added a current limiting circuit to ensure safe startup and operation. Also, these two inductors are the ones that go on each side of the glass. I'll run it from a 12 to 14 volt supply, so I would have close to 40 volt peak AC across the two inductors. So far, I didn't have enough voltage to turn the LEDs on, but that must be enough. But first, I have to finish the mechanical design so I can fit my circuit to it. So here you see my glass with two coil holders on its top and bottom. Let's print it. I'll print my parts using a gray filament. Look how well the glass fits in it. Nice. Now let's design the rest of the lantern. First, I bought this fan with a diameter which fits the glass well, which I'm showing by this black thing on the bottom. Then I designed this beautiful leg so the coil holder falls right into it, and the fan on its bottom. Let me show you a bit more details. See, I designed these fins in there because, you know, the fan rotating creates a vortex inside the glass, and I didn't want my fireflies to stick to the sides of the glass. So I put it in there to hopefully straighten the airflow so that they would fly more nicely in there. Then at the bottom of the fan, I designed this grid so that you don't stick your fingers in the blades. Next, on the top, I designed this vent. Now, this vent might be tough to print, but anyway, I created the same fins to help the straight airflow and a curved ceiling there to help push the air out from the sides. And then on the top comes a beautiful cap. Now this cap has a cavity in there, which is the location for my driver circuit. And last but not the least, I'll hold all the pieces together with these screw rods. Beautiful, isn't it? See, even a monkey can do a mechanical engineer's job. Nope. The monkey couldn't do it in one shot though. All the parts I designed had to be updated. And I had a bunch of difficulty printing my parts because of the lack of 3D printing skills. I had to trash a lot of parts with incorrect designs. I kept breaking my parts and had to re-glue, redesign, reprint. I'll probably just crazy glue this. Just needs some Why do I have to put so much pressure on the delicate prints? In the meantime, I started making the 4 rods that would hold the whole thing together out of some solid brass rod. Tapping these wasn't easy, man. I feel hurt and bruised. Time to design my fireflies, something that can fly. Hi, today I'm having aerodynamic problems. See, I've been messing with the shape of this fly thingy, trying to make it jump up and down in this chamber, but see, I thought the fan blows from the bottom and this thing will go up and down like a fly. But no, the air pressure is not uniform in there. It's like higher pressure in the middle, lower pressure on the surface. So it goes up in the middle and gets stuck on the walls. And if it goes all the way and reaches the fins back there, a high pressure air builds up behind it that makes it get stuck up there and never comes down. Let me ball some papers and see. Oh. See, they get stuck up there because of the high pressure behind them. Well, it does seem balling it has a better chance of rising. Here, I made it kind of ballish like. Come on. Oh, look at it. It's flying. Not bad. Oh, it gets stuck up there still. It seems removing those air straightening blades and let it just cyclone solves almost all the problems. Also, making the firefly like a ball makes sure it doesn't stick because it can roll around easier. So I guess we'll cut these fins off to allow the vortex. There we are. But then I had to make a mesh to make sure my fireflies don't fall into the fan blades and die, which I tried to hand print on the 3D printer hot plate. The properly printed part worked better. In an attempt to go glueless to make my flies lighter, I came up with this, which looks nicer too. Now we have to slide this piece on top of our old piece and just make sure their notches fall into each other. And there we go. We have something like this. Now we place our coil on this part and make it stay in place with a bit of hot glue. And now we make like 10 more of these. Here I have my 10 fireflies, and if I turn the fan on, they don't have LED. You see, they rise to some extent, but if I raise the top a little bit, see they rise much more, which means the top vent is restricting the airflow. What do you know? I had to redesign the top exhaust vent too to make sure the air flows better and lifts my fireflies. I changed the design of the vent because I realized, nope. This new vent is it's printed in two parts and goes together like this and is held together by those long screws. Nope. Here is the final update of the nope. This is hopefully my final top lantern design. See, I put some vents in this top part because the electronics goes in here and I want some of the fan air to blow on my electronics and cool it down. This is my original base design and this is the updated one. See, I had to raise it a little bit higher to provide a greater opening because I realized we need more air to get to the fan to blow the fireflies stronger. And it looks prettier too. And I'm back after a month. Now we build electronics like so, and they will go on the top and bottom of the glass. Nope. First, we solder the current limit circuit. Fine-tuning a bit. Who could have guessed that what you design on paper and simulate doesn't quite match reality? Ow! Transistor is getting hot too. Close enough. Here's the circuit. Let's power it up. Troubleshooting time. Here you go, finally functional. Let's bring close my firefly and see if it turns on. Nope. I guess depending on the angle and how close it is to the winding, it could turn on. What if I bring the coils closer to each other? Let's see. Ooh. It's more uniformly on in the middle. Not very uniformly on the edges, but I guess it's okay. I like the green LED, but I made one firefly with white LED since it was brighter. Let's see. Oh, there you go. Barely turns on. I thought it was brighter. Yeah, see, the yellow-green LED is on more often. Because although the white LED was brighter at the same current, it requires 50% more voltage to turn on. So, because the voltage between the coils is often lower, the green LED turns on more often. So, what color LED should I pick for my fireflies? See, the white LED doesn't turn on very often, but when it turns on, it's a flash of white light. The green yellowish LED is more continuously on, but it's dimmer. Let's ask you. Okay, so around 30% like the warm white and around 70% like the original firefly's greenish yellow. So I'll make 7 of them greenish yellow and 3 of them white. Also, I bring the coils closer in the middle so that there is more uniform magnetic field. I think I should do that. Here's my beautiful coil holder that would go around the glass, like so. I think we have everything we need. Let's just put everything together. The plan is to send the positive and negative powers through the brass rods to the circuit on top.
Stój, śmieciu!
Ej, to tutaj nie ma dinozaurów? W końcu sklepy w każdą niedzielę otwarte.
Pokaż mi swoje towary.
O panie, kiedyś to będzie. Nie wpuszczajcie krzyżaków! A ten chrobry to jest...
Nie no, bez przesady!
15 minutes, set in everyone. Call the goddamn National Guard if you have to. Over?
Kurwa, nie jest to trochę za głośno?
Now listen up.
Zmieniłem słuchawki i są trochę głośniejsze, więc może mi się pierdolić.
Let me do the talking. Got it? Got it. Rookie! All right, everyone. Stay sharp. Let's go!
Inside this box is a 3D printer, and it might just be the world's smallest resin 3D printer. This box is even significantly larger than the sub boxes that are in it. Here we have a box for the power supply, a smaller kit box that says 2. This is a kit assembly, and the main components of the 3D printer come in this little plastic container. So here is our really tiny resin 3D printer that we're going to be assembling today, and fingers crossed this thing actually works. It's only $100 over on Crowd Supply, I think, crowdsupply.com or something. I'll have the links down below. I ordered this back in August and honestly wasn't sure if this was a real thing or if it was gonna fully ship out, but here it is, and it was a really nice surprise to see this show up here in the mail. I can see the metal build plate right here. It is super tiny. Crazy tiny. And this says kit B. Oh, I can tell what this is right off the bat. This is going to be the vat. So it looks like it's a plastic. Yeah, it looks like it's a molded plastic vat here. Very small, very teeny tiny here. A big piece of metal. Inside this little tube is our FEP sheet. And I'm going to open up the main container here. By the way, the name of this is Light 3DP. Yeah, it's a kit assembly, and supposedly it's not too difficult. We'll see how really that is. Here's a whole bunch of screws and bolts and things, a motor and rail, the rod that's going to be used for this, a bag, the actual board, assuming the light display there, that the LCD that's going to power the screen, build plate. Look how tiny this is. Hold on. The Saturn build plate, and here is the Light 3DP build plate. This is a good bit smaller than the Saturn here. Here's the Mars build plate as well, just so you know, typically the smaller size resin 3D printers are the Mars or the Photon. They all relatively have the same size build plate, and here is the 3DP Light. And yeah, this thing is tiny, or the Light 3DP. I don't know if you can tell, but I am so excited to put this together. And normally I'm not a big fan of kit assemblies or printer assemblies, and is one of the main reasons why I love resin 3D printers, because you typically buy them, unbox them, plug them in, level it, and you can start 3D printing. A whole bunch of other plastic parts here. I was expecting these to be 3D printed, and they're not. They're actual molded plastic pieces here. Some more components to this as well. Here is a metal piece of the frame and another bolt. So no instructions. I'm assuming on their website there must be instructions. So I'm gonna grab my laptop and we'll get the assembly for this thing going. While we're going through this build montage, I want to say a big thank you to all my Patreon supporters for your continued support. If you're interested in any of my resin 3D printer profiles, you will find links to that within my Patreon. Thanks again to all my amazing Patreon supporters. All right, we got it all assembled. That took about 30 to 40 minutes, maybe. I'm sure you could probably do it a lot faster than I did. There was a lot of really small areas to try and get into to get the bolts in. Overall, the instructions aren't that bad. I've probably seen worse instructions, but in some areas it wasn't entirely clear. Everything is now assembled. It's pretty amazing to see how everything's held together. There's nothing holding down the vat. It's just some magnets here in two different corners. I might end up installing some additional other magnets in the opposite corners just to give it some better sticking power there. And then the build plate is also magnetically attached here. So just snaps into place, and then you can tighten it down. So let's see if we can get this thing leveled or figure out how we're gonna level this and then get a print up and running on it. It finished! Oh man. Well, there's no easy way to grab this. You just gotta pull from the build plate. All right, let me loosen this and magnetically attaches. Didn't print the little cross pieces inside there or the little pieces that typically stick out there, but it printed. That just means I probably need to adjust my settings here and play around with this bit. Oh man, I'm really excited that this actually printed. So this doesn't come with a spatula or anything like that, so you're gonna need to look into that. I don't even know how to get the print off here. It's so small of a build plate, it's hard to get at it. Holy cow, I think I need to adjust my initial exposure settings. Wow, there we go. Well, at least it's sticking to the build plate really well, and I'm gonna have to get this cleaned up, but it actually, I'm so impressed that it actually printed something, and it looks better than I thought it was going to. And here is my first semi-long print, and it looks so good. Oh my goodness. I can't believe how well this turned out on this little tiny resin 3D printer. So I've had the Light 3DP up and running now for a few days, and I've managed to only get 2 prints really printed on this thing. It does print relatively slow, I'll say that. It's kind of hard to judge exactly how long each time prints, but I will say the on-screen indicator before you run your print, it's going to tell you the estimated time. As far as I've checked with at least 2 of the prints, it's been fairly accurate coming in. One of those being almost exactly an hour and the other being a little over 2.5 hours long. One of the challenges that you're going to run into with this is it's obviously a very limited build volume, so you can really only print like one thing at a time unless you're printing extremely small things. So I was able to print a miniature from Loot Studios, and I was able to fit the entire miniature on there at its full default 32mm scale on the bed, and then I had to separately print the base on this. So it was 2 separate print jobs that I had to run on this machine to get this tiny miniature figure, and the results look impressive. It's not bad, better than I was honestly expecting from this little machine. I think it even looks better than the prints that I was getting off of the Monoprice Mini, I think is what it was called, that I reviewed a few years ago. That was like, hey, this is amazing, it's a really affordable, cheap resin 3D printer, and it actually prints. The results on this look light years better than that machine, and I think that machine even costs more than this does currently. And then the file that I'm most impressed with is this miniature Joker bust by Doses 3D, which is probably the newest Patreon that I've been taking part of, that I absolutely love his models on. Everything comes pre-supported, and this is his latest release for November. It's this Joker bust along with a number of other files. But I printed this here in each of the components, the hat, the bust itself, and then the base, all printed individually, separately on this particular printer here. And I ended up using this Elegoo mint green for the print. And again, the details look fantastic at 0.05mm layer height. I'm honestly impressed that with the rod, that the really thin Z-rod that's in place there, it's not wobbling or doing anything crazy like that. The print quality looks good. I am seeing some layer line issues on the in certain angles when you look at it. I'll try and get some close-ups of this where you can see the stepping, but outside of that, it looks great, especially for $99 in a kit 3D printer. By the way, this is all open source. I don't think I necessarily mentioned the price. It is $99. There are a few different add-ons, and it is pretty basic when it comes to the machine itself. So I ended up buying the actual power adapter so that I didn't have to worry about figuring out what kind of adapter I would need to plug into that. So that's an extra cost, but it does come with the build plate, the VAT, the FEP sheets. It came with an extra FEP sheet. The assembly process, again, I think only took me like 30 minutes to an hour to assemble it. Well, really wasn't that difficult. I did run into some issues when it came to actually getting the prints sliced and up and running on here, and let me explain how that all worked. So for me to slice a file to have it ready to print on this tiny 3D printer, it's a little bit more complicated for me because I'm on a Mac and I don't have a PC in the household. Well, thankfully I did, but If you're on a PC, it's much easier. They have a tool that they've developed that will allow you to take a zip file that you're able to get out of Chitubox. So you're going to slice your file in Chitubox. Don't worry about all the profile settings. All you really care about is the actual build volume of the machine so that you're not putting your file outside of the build volume. It's going to generate a zip file. You're going to extract as a zip. You then take that zip file and run it through their conversion tool, which will take all of the individual PNG files and turn those into Windows bitmap files. Now for me on my Mac, the workflow process was a little bit more cumbersome, and it all comes down to software issues on my end. I ended up downloading a few different types of software to try and convert the PNG files to bitmap. That didn't convert it to the proper formatting, which is why I was having print issues initially when I was trying to get the machine up and running. So if you end up getting this machine and you notice that the screen is actually working and you can go through all the menus, but when you actually print a file, nothing's showing up, it's because the conversion between the PNG and bitmap is not processing correctly. So I tried two different softwares. I tried the preview application built in natively to Mac, which converts PNG to bitmap. It all boils down to it not converting to the proper formatting that's needed for this printer to actually print those files. Thankfully, I had this super tiny PC that I managed to find that someone sent me years ago that I never ended up doing anything with. I ended up putting their conversion software on this machine, and it's not a Mac, it's just I put the sticker on there because it looks like a mini Mac. But I was able to then properly convert those over, load it on the USB stick, and then get my prints going. By the way, you are also going to have to buy your own micro SD card or SD card reader if you're interested in getting this machine. It does not come with one. I was looking all through there, couldn't find anyone. And then it's also not going to come with any of the extra supplies like a plastic scraper or a metal spatula there, scraper, to get your prints and clean up things when you're working with the printer. And by the way, these standard plastic spatulas that come with most of the resin printers, it perfectly fits inside this vat, like exactly fits inside there. It's a really beautiful thing. Another interesting thing about this printer is that everything's just held in place by magnets. The build plate is just magnetically attached and it locks into place. So when you actually go through the printing process, it's going to ask you to level the build plate. It does that after every single print. You need to re-level because you have to take this out in order to get your print off and then put it back in place. Once you go through the process of actually defining what you want to print and then defining the settings, that's right, during this actual print process, when you go to print the file, you define what the parameters are, what layer height, what exposure settings, what bottom exposure settings you're going to select. And it's only 3 settings that you have to define, which is kind of cool. And then it's going to ask you to put the vat in, and it's all, again, magnetically attached. And then you pour your resin in and it's good to go. For the vat, there's only 2 magnets in each corner. And I honestly think it does a pretty dang good job of holding it in place. I thought maybe I was going to need to go out and buy some extra magnets and install those, but I really haven't seen any issues with this coming loose, and it's pretty strong when it comes to the magnetic forces at play there. So I don't want to call this a review of the Light 3DP because it's not yet. I feel like I need to play around with this a good bit more, print with it a good bit more. But I did want to call it, like, who exactly is this for? And in my mind, it's really for anyone that's out there that is interested in tinkering with things and building their own machine from the ground up, that's interested in it being a completely open source product that you can then go and build things on top of. It doesn't come with an acrylic case or anything like that. So thankfully my print area here is pretty well shielded from direct sunlight because I do a lot of resin lapses. Oh, and the resin lapse cable won't work with this. The light source in the bottom, I don't think is strong enough to trigger the actual camera trigger, which is unfortunate, but maybe I can figure out a way to work around that. But this machine, it prints decent and it prints well for the price point. However, if you're interested in resin 3D printing, I can't say go out of your way and buy this. You're gonna have a much better experience spending an extra $50 to $60 and buying the Voxelab Proxima or what Polaris or whatever the lowest priced resin 3D printer on Amazon is over something like this currently. Just avoid that mono price mini thing. It's not a very good resin 3 printer. Also, I did want to mention that the community behind this, there is 2 different Discord channels. There's a subreddit for this as well. Everyone that I've interacted with over there has been extremely super helpful with all of this and answering my questions. And there's other people that have been joining that have just received theirs and their questions have being answered. It's a very small community currently because I don't think there's a whole lot of these out in the wild just yet. But I found out about this back in August. I put my order in and just received it here at the end of October. And so I would expect, you know, around a 2-month lead time there, all depending on how many they have on hand that they're shipping out at any given time. But I do think it's really cool to have such a small, tiny resin 3D printer that actually prints proper things. I'm planning on attending the Rochester Maker Fair here later in the month in November, and I'm hoping to be able to bring this on hand with me there so that I can actually show off some resin 3D printing while I'm there in person and not have to worry about a huge resin 3D printer, or even something like the Elgu Mars, where if some resin spills, it can make a gigantic mess. This, on the other hand, can barely hold any resin. The amount of resin that's held inside this vat, I easily waste more resin just taking my prints out and cleaning them off of the Frozen Sonic Mega 8K. It's ridiculous how little resin this thing actually uses. But if you're interested in more information about the Light 3D printer, I will include links down below where you could find that. And if you're interested in purchasing it, that's where you'll be able to pick it up. Again, I'll have links to their Discord as well, so that if you have further questions, you can check that out and answer, you know, see whatever thing's going on there if you're into that sort of thing. I'll be continuing to print with this on and off. I'm not entirely sure what I'm going to do with it. I have a few projects in mind. If you have some suggestions, let me know down in the comments, because I want to see what I can potentially add on or build on for this unit. Or I have one other use case that I really want to test out and see if it will actually work and not make a gigantic mess or ruin something of mine. Hey, thanks again for watching, you guys. Hopefully you enjoyed, and I'll see you next time. Bye now.
Hi, I have been sitting by my setup here, working every day from home for hours at a time. Hours!
This has caused me lack of stamina, physical weakness, high cholesterol, blood clot in leg.
So I was a little bit worried about my health. And therefore, I bought one of these under-the-desk miniature thread mills. Yeah, ignore those. It's from the couple of times I almost fell off today. And I heard a bunch of good things about it, but I have to experience it for myself. See, I have one of these raising desks I had bought a couple of years back, and I thought working behind it, standing, make me lead a healthier lifestyle. But I was wrong. I realized that just standing a few minutes behind it, I would fatigue. My back hurt, my joints, muscles, I get tired easily. So I almost never raised my table and kept sitting for the entire workday. But I knew one thing, I could walk for hours without stopping and not feel fatigue. So I bought this guy, and hopefully now I can walk and work and hopefully not die in the process. I know this might not be for everyone. I know some people that they have to stop and look at their phone and they can't look at it while walking. But I don't think I have any problem with this, so we'll see. Now, this guy I bought, which is not sponsored of course, I just bought something random with good reviews. All I'm really asking from this guy is to not fail under my weight, which is, taking clothing into account, I would say I'm around 200 pounds. And what I expect from myself is walking all day instead of sitting all day, which would make an infinite improvement in my lifestyle. Oops. So let's get back to me in a month and see what happens. Can I continuously walk on this thing while working and do whatever I want? Will this thing last under my feet? And will I lose weight, and how much? I'll get back to you on that. Look at this. Why am I losing so much of the sole of my shoe for some reason? Am I not stepping well? Well, better my shoe than my skin. So I've been walking for a few days now and it's actually been quite enjoyable. But something I noticed is that I can't use my old headsets anymore because I get quite warm, and with these foams on my skin, it sweats under the foam and hurts my skin. So instead, I bought one of these sport headsets that goes straight into your ears and keeps your... Oh shit! Oh. The hell was that? It zapped me straight in the ears. So with these headsets, you won't have any heat. What the f? What's wrong with these headsets? They keep shotting me in the ears. Such a waste of money. It's not a headset problem, is it? I think I figured what the problem is. See, me walking on this thing, my body picks up charge from friction. Basically, this thing is like a Van de Graaff machine. And the outside of these headsets are made of plastic, so there's no direct connection between my skin and these headsets. So my body gets to build up voltage high enough that eventually it discharges to the ground through these headsets. And of course, this is a wired headset. That's why this is connected to ground. And that's where you would have benefited from a Bluetooth headset. So I decided to use one of these static discharge bands. One side of it on my skin, and the other side I just shove it into my metal table to discharge me to the table. And now I can safely use my headset without getting shocked. But now there's a different problem. Look at my display. It keeps turning off and on. Damn it! I don't think my metal table is connected to earth properly, so it picks up charge with my body and probably discharges somewhere that creates great electromagnetic field that interferes with the display, and it's shutting down, which means I have to connect it to a proper earth. Well, my extension cord does have earth. Yeah, this whole table is powder coated and isolated too, so I directly alligator clip my wire to earth and we should be fine. I should probably find a better earth connection to myself later, but hey, so far so good. No more display shutdowns. On the bright side, filming this part, I walked over 2.3 miles or 3.5 kilometers. It's been a bit over a month now, and this needs some service. Did you wonder where all the sole of my shoe that was worn out on the belt went to? Well, here it is, all inside of this thing. I have to vacuum it well. I feel like some of that garbage may have gone into the motor too. Of course, turn off the power before committing anything like this. Well, let's turn the motor on to see if it makes any funny noises. It did feel a little bit strange. It was shaking, but it went away. Anything falls out of it? Maybe turning at fast speed release the garbage inside of it. Okay, sounds good. Do the monthly lubrication. The motor doesn't sound right. You hear it? I'm servicing my treadmill again after another 2 months, and look at all the gunk that got onto the roller of this thing, which are basically plastic melted from the sole of my shoe. And you know, all the hair and garbage that I shed. So I guess I cleaned them all up and vacuumed the whole thing and oil it, and we'll be good to go again. Look at this. Let me see if I can measure the belt's temperature. 52 almost. That's probably the reason the oil starts smelling, because it's warm. And probably the reason the sole of my shoe is melting away. It's not super warm, but I wish there was a way to keep the belt cooler. Maybe I should just blow a fan on it. Something like this, maybe? Okay, it seems like the fan is keeping the belt temperature closer to like 43 degrees or something. Man, this is not convenient. Every couple of months I have to open the whole thing up and vacuum the garbage out of it, and now the motor is stuck. The whole thing doesn't turn anymore. I have to see what's stuck and fix it. What is... There is molten plastic coming out of the motor. Yeah. Okay, we got it out. The rotor seems to be totally stuck. Oh man, what is all this over the rotor? Did the motor overheat and epoxy melted or something? Look at all the garbage I got out of the motor. It's clean now. Hopefully all those molten stuff was not the coating of the wires and they are not shorted, otherwise the motor is doomed. Well, it's back together now. But if you haven't opened and closed the motor yet, just note that all the parts of the motor have to go together in the same direction, so I marked them to make sure they align. Well, it's turning freely, but the question now is, will it turn? Yup, turns smoothly. I guess the motor was getting super hot. Look at the